In this session, we are going to present melting point subject in organic chemistry. We want to talk about melting point and how it is important for us to know the melting point. So you know that the melting point is a great way to analyze a solid, to identify unknown solids, and to use it to confirm the purity of a solid that you isolated and purified. So, first of all, we want to say what is the melting point of a solid. At the melting point, solid and liquid are coexisting and both are stable. So it means when a little bit of a solid changes to liquid, a little bit of liquid turns back to the solid. So they both coexist at that temperature, which we call melting point. So in the other point, or the melting point is the temperature at which solid and its liquid have the same vapor pressure. So vapor pressure is the pressure that a matter exerts to a medium around it. For example, water has a vapor pressure. Alcohol has a vapor pressure. Also, solid has a vapor pressure. But vapor pressure is different at each temperature. At the room temperature is different from a temperature when you increase the temperature. So the vapor pressure of both solid and liquid are the same at the melting point. That's another definition for melting point. Vapor pressure is a kind of indication for any material that we need to know that it's gonna change with the temperature. When we increase it, when we increase the temperature, the vapor pressure is gonna change. Usually, it's gonna decrease vapor pressure by increasing the temperature of the surrounding. You know that the solid has a internal attractive force inside it. So it means if we have a solid like a salt between Na as a sodium and Cl as a chloride, there is an internal force. When we increase the temperature, we add the kinetic energy inside the solid. So at the point of melting point, this kinetic energy is overcoming at the internal force between Na and Cl, and it changed the phase of the solid to liquid. So you see that at solid we have very strong force between Na and Cl, but in liquid form there are a vibration between Na and Cl, and in gas there is no force or a very tiny force between different atom or molecules inside the compound. So we want to know what is the advantage of the melting point, why we want to use the melting point in organic chemistry. It helps us to understand how pure our material is. Melting point, as I mentioned, is a physical property of a solid compound. You will see the melting point is sharp for pure compound. The more pure a solid is, the sharper the melting point is going to be. So that's why the melting point makes a great tool. Not only tell us whether or not the compound matches the literature value, which we can use it to uh, identify unknown compounds, but it helps us to understand how pure our material, our particular sample is. So if there is impurity inside our compound, the melting point is gonna change. It's not gonna be the same melting point as we have the pure material. So pure compound shows a sharp melting point, usually just by 1 degree. But when we have impurity, that compound is going to have a range of 2 to 3 melting point. It means it starts to melting and it completely change to liquid, and with the 2 to 3 degree, when you see that this takes time to get to the liquid condition. And melting point of impure compound is usually lower than the pure compound. This is called melting point depression. So consider that we have 2 compounds, A and B. You see that A has a melting point temperature of A, and B has a melting point temperature of the B. For the first condition, if compound A is contaminated with 20% of B, you see that the melting point is going to change to C. It is lower than A, and we don't have a sharp melting point. I'm gonna show you in the future. And if we have a compound B pure and we contaminated with 20% A, you see that it's gonna be lower than the B. And there is a point that we call it eutectic point, which is the point that it's lowest. It is the lowest point of melting point in the between A and B. So in the eutectic point, we have a mixture of A and B. So, for example, if we have a NaCl and KCl, these are 2 compounds. So for that mix, the eutectic point of that mixture is gonna be like 60% NaCl and 40% KCl. So it is not the same for the other compound, like lithium chloride and KCl. They have the different eutectic point. So between 2 compounds, it's always be 1 point, like 40% KCl and 60% NaCl is gonna be always constant between these 2 compounds. And for lithium chloride and potassium chloride also is gonna be another eutectic point. It's not always 60 and 40%. Maybe it's 50-50. We don't know. Maybe it's 30% and 70%. So for another example can be a eutectic mixture of ice and salt, which is 70% ice and 20% salt. So if you use 77% ice and 23% salt, you can decrease the temperature to minus 20 degree of the Celsius, so lower than the 0. So that's why we can when we are at the old time when they were making ice cream, they use the mixture of ice and salt to decrease the temperature for lower than the zeros to make ice cream. It's one of the example of application of that melting eutectic point. So in our experiment, we are going to use benzoic acid and 2-naphthol. And benzoic acid has a melting point of 100 degree to 123 degrees. And naphthol also, it has a 121 to 123. We have 5 different compounds, pure benzoic acid and pure 2-naphthol, and 3 mixture of benzoic and naphthol, 10%, 90%, 50-50, and 90-10. So to prepare melting point tube, we need to use capillary tubes, which are very narrow tubes, and they are sealed on one end, very similar to test tube, as you see here. These are the capillary tubes. So they are open in one end and sealed on the other end. What we want to do is to load tube with the sample. We want to put this sample inside the test tube and pack the powder tightly inside the tubes, as you see. So we scoop up powder inside the narrow capillary tubes. Before putting powder inside these tubes, we want to make sure the compound that we have is not in the form of the crystal. It should be in the form of the powder. And we want to tap on the counter so the compound should be tight. It should not be any air pocket inside between powder, because when there is a air pocket inside the powders, they are not heated evenly. In this slide, you see that we have an apparatus for melting point. In this apparatus, it has a couple of things, like a heating block. As you see here, it has a heating block where we slide down this test tube or capillary tube, and we have also the temperature that we record the temperature of the heating, and we also can control the rate of the temperature. So before 80 degree for these two compounds, because we are sure that their temperature is above 120, the rate of the heating is 5 degree per minute. But when we pass the 80 degrees, we want to lower down the rate to 1 degree per minute. So we place the tubes inside the apparatus and see the tubes when they get heat. So we heat the sample and we control the heating rate. We do not want to heat too quickly because there is going to be a lag between heater and compound. So maybe like if we heat it too quickly, we record the temperature higher than literature values. We need to watch the thermometer. So if the heat changes too quickly, we can't record the actual number. We are going to watch the powders as they are heating up. We record two data. First, we look at the powder. The first sign of melting, uh, and it is when the crystal start to look wet. So when the crystal start to look wet, the starting point of melting. But before that, you will see that the crystal start to shrink a little bit. That is called sintering temperature, which is not our aim to record. We ignore that temperature. We don't want to record the sintering temperature. We want to record the first temperature that the powder start to become a little bit wet. Then it changed to a little bit, adds the liquid when we increase the heat, and at the end we are gonna record the very last crystal that changed to a liquid phase, and at that point the crystal is disappearing. So we are in. So at that point, all the metals inside the test tube is gonna be liquid. So it's a range that we are gonna record between the starting point, which is the point that the powder is become a little bit wet, and the final point, which is the very last uh, uh, amount of powder is gonna change to liquid. So we record both temperature. When we do that for our five five conditions that we had for our materials, we come up to a table. So we know that the melting point for the for our two naphthalol naphthol is 121, and for our benzoic acid is also 121. So we see that when we have a mixture of the compound, we have a range here. For 10% mixture, we have this range, and for 50% also we have this range. For this mixture, the eutectic point is 50-50, but in different with the different compounds, we have a different eutectic mixture. So we are gonna record all the melting point here. At the end of our experiment, then we can draw this blue and red line, as you see. So we have the 10% mixture, we have the 50-50% mixture, and we have 90-10% mixture. And as I mentioned, we have the 0, which is 0 for one of them, which is 100 for the other one. When we have 100 here, it means the other one is 0. So both ends of this curve are pure materials. Here is the pure 2-naphthol, for example, and here is the pure benzoic acid, and these are the second point, and this is the third point, and this is the fourth. And you see that the broadest melting depression we see for the eutectic conditions. At the end of the experiment, you see that the benzoic acid, 2-naphthol, and any heavily contaminated waste are solid waste. If we have a broken capillaries, is also we are gonna throw it to the waste container for the glasses, and then at the end we are gonna turn off the apparatus. And at the end, this is the duty of the TA. And thank you for listening to our this session.